Hello all. Today we will be discussing about the CPU scheduling. So when we have a set of processes which arrives into the system for getting it processed, initially it will be joining to the job queue. And if a particular process requests for either IO or CPU, it will be directed to either the ready queue if it requests for CPU or to the IO queue if it requests for IO. So, in which order the process inside the ready queue enters into the CPU is what we call it as the CPU scheduling. So, when we just direct these processes into the CPU, the process makes sure it completes its entire execution and then comes out, and that kind of scheduling is what we call it as non-preemptive. In case if a process could allow any other process when it is partially completed, then we call that kind of processes scheduling as preemptive type of scheduling. So we have several algorithms to make sure in which order these processes enters into the CPU through these algorithms. So the first algorithm is the first in first out. We call it as the first come first serve also. So it is purely non-preemptive in the sense a process enters into the CPU, complete its entire execution and then only it goes out. In between it will not halt for a while or it will not allow any other process into the CPU. The second is if we allow only the processes in first come first serve basis, what happens to the processes which has very least job and have arrived at last? So we have to make sure we have to give some that is concerned to the processes which has the least job. So for that the next algorithm is introduced, and that is the shortest job first, where the processes which has arrived will be entering into the CPU with very least job. So whichever process has the least job, it enters first, and in that sense it can be either preemptive or non-preemptive. The first option is the non-preemptive option, where the shortest job is selected, it enters into the CPU, it completes overall and then it exits. But when a process is already inside the CPU, another process comes with another least job, then what happens is the process which is already there in the CPU can preempt. It allows the next process which comes with a very least job, and then it halts for a while, let the other process completes, and then the previous process resumes back. And that kind of scheduling algorithm is the shortest remaining time first, which is preemptive. And the priority scheduling, a process can be let into the CPU based on its priority. Whichever process has the higher priority, that process goes in. So this can be either preemptive or non-preemptive based on the situation. So far we have seen three algorithms. The first just lets the process into the CPU based on the arrival time, that is the first come will go into the CPU first. And whichever process has the least job, it enters first, is what the shortest job first scheduling says with preemption and non-preemption. And what will happen to the processes which comes with a higher priority? So we are not going to give there is option only for the FIFO or for the shorter job. We have to just give access to the processes which has higher priority also. So for that the priority works. So finally comes the round robin scheduling, which is the most effective algorithm, where it gives equal opportunities for all the processes. Make sure every process enters into the CPU and spends some time inside the CPU, and then it comes back and then joins the ready queue. So that time is what we call it as the quantum time. Suppose if a process has to enter into the CPU, it will be processing only for a quantum time. It just comes and get added to the ready queue. The next process goes, it spends the same quantum value. Likewise, it will be keeping on going. So this is what we call it as the round robin scheduling. So the key terms will be the arrival time, the burst time, completion time, turnaround time and waiting time. So before into the solving, we will see what these are. So when a particular process enters into the ready queue, we just specify it with a timestamp, and that time is what we call it as the arrival time. And if a process would like to spend some amount of time inside the CPU, and that is what we call it as the execution time, that is the burst time. And a process has entered, it has waited in the ready queue, and then it has entered into the CPU. By some time it might have completed its execution. So, and that time is what we call it as the completion time. Now we have the turnaround time from the time of the arrival till it completes its entire execution. So far how much time it took, that time specification is the turnaround time. And finally we have the waiting time, the time which a process spends inside the ready queue waiting for the CPU. Okay, so how we can calculate these? So we have two formula. So we know the turnaround time is the total time spent from the time of arrival till it completes. So it is the completion time minus arrival time. And the waiting time is, so far we know the total, that is the turnaround time. From that, if we just subtract the execution time, that is the burst time, we will find the time, and which is the waiting time, the time which a particular process took being or residing inside the ready queue or waiting inside the ready queue for the CPU, and that is what we call it as the waiting time. So far we have seen the key terms, the types of schedulings, the algorithms and the formula. Now let's move on to the solving part. The first is the first in first out, where the inputs will be the processes with the process IDs. The arrival time is given. If the arrival time is not given, we are supposed to assume it as 0, assuming that all the processes has arrived at the 0th millisecond. And we have the burst time, that every process will take a particular time inside the CPU for its execution, and that is what we call it as the burst time. So these are the inputs for which we are supposed to just check how these processes enters into the CPU, in which order these processes enters into the CPU and get it processed. So based on the arrival time, we shall just make these processes to enter into the CPU. As of now, we don't have the arrival time. So we have assumed that the arrival time is 0. So what we do? We take the process ID. Based on the process ID, we just let these processes to execute inside the CPU. And here is what we have. There is the Gantt chart representation, which shows at what time a particular process enters into the CPU, how long it took, at what time it just went out of the CPU. So this representation is what we call it as the Gantt chart. So far we have the processes. We know these processes arrived at 0th millisecond. So the order in which we are going to just send it is the process ID. So the first process is P1. Its burst time is 2. So the first process starts with 0 millisecond and ends up by 2nd millisecond. Now the second process takes 5 milliseconds. So P2 starts by 2 and its burst time is 5. So 2 plus 5 on the whole, it completes its execution by 7th millisecond. So P2 takes 5 milliseconds inside the CPU. Now the third process arrives. So it has only one burst time. So from 7, if it takes 1 millisecond, it ends up by 8 milliseconds. The final process which enters into the CPU is P4, which takes 7 milliseconds inside the CPU. So 8 plus 7, overall it is 15. So let's just check for the completion time of each processes. The first process completes by 2 milliseconds. The second process completes by 7 milliseconds. The third process completes by 8 milliseconds. And the fourth process completes by 15th millisecond. Now when we calculate the turnaround time, we know the formula. It is the completion time minus the arrival time. So it is the completion time of each process minus the arrival time of this process. So similarly, for 4 processes we have got the turnaround time. Now we have to calculate the waiting time, that is the total time spent minus the time spent inside the CPU. So that is what the time it waited for the CPU. So it will be the turnaround time minus the burst time of a particular process. So finally what we will be calculating is the average turnaround time of a particular process and the average waiting time of a particular processes. But there is all the processes. So far the entire processes P1, P2, P3, P4 has taken 8 milliseconds on the whole, on an average, and it has waited for the CPU for 4.25 milliseconds. So this is how the FIFO works. Now let's solve the same FIFO algorithm with the arrival time. So assume that the processes has arrived at so and so timing. So when we have arrival time, then it is based on the first in first out order. So which process has come first? The process which has arrived first has to be considered as the process which has arrived first. So that is the first in process. So first we are going to process the process P3 followed by P4 and then P1 and then P2. Remember, this FIFO is also non-preemptive. A process enters, completes its execution, and then only it allows the other process. Whichever time the other processes arrives into the ready queue, it never bothers, but it completes and then only allows the next process. In that case, what we do is we have process 1 which has started by we have process 3 which has started by 0th millisecond. Its burst time is 1, so it completes by 1. So the second process which enters into the CPU is P4 because it arrived by 1st millisecond. Yes, the process has already arrived. So P4 takes 7 milliseconds. So 1 plus 7, it completes by 8th millisecond. We will see till 8 milliseconds so far how many processes arrived. Yes, P1 has already arrived by 5th millisecond. So it is already there in the ready queue. Pick that process. Let it inside the CPU. Now P1 takes 2 milliseconds inside the CPU on the whole. So it is 8 plus 2 which is 10. Now by 9th millisecond this P2 has come. So already we have a process in the ready queue. So we take this P2 and then process it for 5 milliseconds. So 10 plus 5 is 15. So now if we check for the completion time, P1 completes by 10 milliseconds. P2 completes by 15th millisecond. P3 completes by 1 millisecond. And P4 by 8. And as usual, the formula for turnaround time is completion time minus the arrival time. So we have the turnaround time for all the processes. Similarly, the waiting time is the total spent, that is the total time spent minus the time spent inside the CPU. That is the time it has waited for the CPU. So on the whole, on an average, all the processes has completed its execution in 4.75 milliseconds, and all the processes on an average has waited for 1 millisecond for its turn to enter into the CPU. So this is how the first in first out with the arrival time works. Now let's see how the same kind of processes executes with the shortest job first algorithm. Now we have the same processes considering no arrival time. So assuming that all the processes has arrived at the same time. Now we have to make sure which process has the least job. So when we just look into the scenario, P3 has the least job, followed by P1 and then by P2 and then by P4. So this is the order in which the processes enters into the CPU. So by 0th millisecond P3 will start because it has the least job. So it has 1 burst time. So it enters into the CPU. It completes its execution by 1 millisecond. The second process is the P1, which has the next least job, which has 2 burst time. So it starts by 1 millisecond and it takes 2 milliseconds inside the CPU. So it will be completing it by 3 milliseconds. Now the next process to enter into the CPU is P2, which has 5 milliseconds. Now 3 plus 5 is 8. Now finally we have the process with the highest job. There is the burst time. So it is P4. It takes 7 milliseconds. So totally it is 15. Now if we calculate the completion time of the processes, P1 has completed by 3 milliseconds. P2 has completed by 8 milliseconds. P3 has completed by 1 millisecond and P4 by 15. So the total there is the turnaround time is completion time minus arrival time. So on an average all the processes has took some 6.75 milliseconds to complete its entire execution. So the waiting time is turnaround time minus the burst time. So on an average every process has waited for its turn for 3 milliseconds. So when we just cross check the FIFO, we had 8 milliseconds, which is the average turnaround time, and 4.25 was the average waiting time. So if we look into the shortest job, so the turnaround time is also reduced, the waiting time is also reduced. So this SJF gives better results than the FIFO algorithm. Now let us move into the SRTF. That is, when a particular process is given with the arrival time, we make sure based on the arrival time we have to process these processes. Suppose a process arrives at 0 and then the next process arrives by 2 milliseconds, for example. If the first process has 10 milliseconds, it can process only for 2 milliseconds. It checks for every millisecond whether any other process has arrived or not. If at that time, when the second process arrives, it compares its remaining burst time with the newly arrived process burst time. There, whichever process has the least burst time, that process has to make sure enter into the CPU. Their preemption happens, and that's what we call it as the shortest remaining time first, because at every millisecond, whichever process which is there inside the CPU, its burst time and the newly arrived the process burst time will be compared. Whichever process has the least burst time will be entering into the CPU by just throwing the previous process back to the ready queue. The newly arrived process which has the least burst time will enter into the CPU. Okay, so we are preempting the processes. So let's see how the processes just do. So I am just adding one more column, that is the remaining burst time, because at every millisecond we have to make sure how many processes has completed how many milliseconds inside the CPU. So that if it has 2 burst time, if it has completed 1 millisecond, then it has 1 more millisecond to get it processed. So to keep track of that, I am just adding this column. It is optional, it is your choice. So the first process which enters into the CPU is P3 because it arrived by 0th millisecond. So 0, it has only 1 millisecond. Yes, it completed its execution. The next process which enters into the CPU is P4. It has 7 milliseconds. So check for the next process's arrival time. It is 5. So from 1 till 5 he can process how many milliseconds? So it is 2, 3, 4, 5. He can just process for only 4 milliseconds. So what we do, we complete its 4 milliseconds of job. This P4 completes 4 milliseconds. So at the 5th millisecond, this P4 will have 3 of its burst time which is remaining, because it has 7 milliseconds. It has spent 4 milliseconds inside the CPU. It has remaining 3 more milliseconds to get it processed. Now, by the 5th millisecond, we have the process P1. Now our job is to compare the burst time of the newly arrived process with the burst time of the already existing process inside the CPU. Now, P4 is already there in the CPU, but it has 3. The newly arrived process has only 2. So what we do? We just take this P4 out. We just get it added to the ready queue. Now the process which has the least burst time enters into the CPU. Okay. So P1 enters. So the next arrival time of the process is 9. So it has remaining 4 milliseconds, but it has only 2 milliseconds burst time. So till 5 to 7, it completes its execution. It is over. Now at 7th millisecond, there is no process which has arrived. So we are already done with P4. It is having remaining 3. P3 is entirely completed. I am just taking it out. P1 is also entirely completed. I am just taking it out. Now till 7th millisecond, no process has arrived, but the one process which has burst time still to be getting it processed is the P4. So what I do, till the next process arrives, till 9th millisecond, I can just process this P4. So what I do, I just take this P4 inside, I get it processed for 9 milliseconds. So the remaining burst time will be 1. Now at the time, I compare the newly arrived process and the already existing process. Whichever process has the least burst time, I am going to just go with that process. Now P4 has the there is burst time which is very less than P2. So what I am going to do, I am just going to continue with P4. So I am just adding this one here. So it will be completing its execution till 10th millisecond. So the remaining burst time is 0. Now we have only one process which is left. P4 is also done. So that process is P2. Till 10th millisecond all the processes has arrived. So no need to check for the remaining burst time since all the process has completed already. We have only one process in the pool and that is P2. So P2 takes 5 milliseconds. So it is 15. So if we just calculate the completion time of P1, it is 7. P2 it is 15. P3 it is 1. And P4 it is 10. So the turnaround time is 7 minus 5. That is the completion time minus arrival time. And the waiting time is turnaround time minus burst time. And on an average, the turnaround time is 4.5 milliseconds. And the waiting time is 0.75 milliseconds. The same process, the same example we took for the FIFO, it was 4.75 and 1. So when we compare it with SRTF, it is 4.5 and 0.75. Okay, comparatively the waiting time is reduced. But if we check, the turnaround time is also reduced. And so we are done with the FIFO and SJF. We'll continue with the priority and round robin in the next video. Thank you.